Hello, welcome to Lancaster Hi-Fi. Kind of on hiatus from doing my usual high production videos, so I'm bringing you a low production video today of what I'm working on. And today I'm working on a Sansui 1000 stereo receiver. This is a thing that I picked up last summer when I was back in Arkansas. And I did a bunch of work on it last summer, but well, it's still a work in progress. I was specifically at that point having problems with the phono preamp. It is a tube receiver, but has a solid state phono preamp. And I've been having conniptions with it, still haven't got it worked out. And I'll talk just a bit about that today, but not much. Today, my focus is on the tone controls. And I've been working on tone controls on a couple of other amps, including a Westinghouse console amp and my Peco SA40, which I featured on a couple of videos on this channel. Well, let's get to it. Let's check out the Sansui 1000. Here it is, standing up on my bench on its side, the back off. And it is partially dismembered, especially the tone control part, which would be here. And I've got the tone pots here and these sort of early style integrated circuits that had resistors and capacitors in them to do the sort of filtering that was desired for tone controls. And to the extent that, values may have drifted over time and so on, it can be advantageous to replace these. But as long as you're replacing them, hey, how about addressing the very design, the original design of the tone control in the first place? So let's go to the schematic. And here I have a schematic in LTSpice. And if you're not familiar with computer modeling of circuits, LTSpice is a great one because A, it's free, and B, it can do a lot of stuff. And if you can't find something that it should be able to do, then you can often find online a way to do it that somebody else has figured out, a model, something, etc. All right, so here I have the preamp circuit for the Sansui 1000. This is the original circuit here at the bottom and my modification here at the top. The tone control stuff is here and here. Now this is the original as it was laid out in the original schematic, although you can see a broken bit here. I have been having trouble reproducing the test results with this little capacitor in circuit. So that can be a problem with LTSpice or with any computer modeling, is that there may be a mismatch between testing and reality, which may mean that when I go back into my original, or I go back into my modified circuit, where I've also clipped out that 20 picofarad capacitor, I'm sort of keeping in mind that I may need to add back a capacitor in order to compensate for stray capacitance that is in the real circuit but is not in my modeled circuit. Now there's another thing that you will notice here where I have a straight line going from this tube to what will be the input stage of the power amp over off screen. And here there's a bunch of stuff in the original circuit. This is a low filter, this is a high filter. This would have, been essentially a rumble filter, and this would have filtered out radio static or crackly records. Nobody uses these anymore. And the way they've been implemented here even when they're out of the circuit, supposedly, so you can see these capacitors are bypassed here, and this bit is not connected to ground, they still interfere, they still interact with the circuit in a way that I don't like. And so I would just as soon get rid of them. On the other hand, as I'm working on these tone controls and recognizing that it can be a bit difficult to figure out just with the tone control itself where the so-called flat response is and should be, and it would be really nice to simply have a tone bypass, you know, be able to flip switches and be able to bypass the tone controls entirely and come out with approximately the same gain and maybe even just overall flatter response. So I can kill two birds with one stone here. I can get rid of these here. So you can see I've just deleted them from there. But I can use the switches, and instead of just using one switch for stereo in each of these cases, I can use one switch for one channel and the other switch for the other channel so that I can do bipolar or dual pole switching. So here you see that I have a bit of circuitry up here, including a feedback. So we're going, so see in my sort of flat circuit here that we're going through a 0.1 microfarad capacitor. We've got a grid leak of 270K. All right, we're going to the grid of the next tube. And we've got this 330K going back after the capacitor to the grid of that tube. Now over here we've got a loudness switch and we've got volume control, and that's relatively complicated simply because I've got to have it so that I don't have a dial that I can turn on my computer model. So right now it's set to about middling volume, pretty high volume, but middle volume. Loudness is off, and it's set to flat, and we can look at the response. This is a graph of the frequency response going from 10 hertz on the left to 100 kilohertz on the right, and we see 7 dB here. This is the ratio of output to input, so this is showing us the gain in dB. At this volume setting, that's about 12 dB. And if I turn the volume all the way up in the circuit, I get up to about 34 dB. Now I can show you what happens when I switch over to the tone controls by moving these jumpers down here like a slide switch. I've arranged it so that it looks sort of like a slide switch. I hit the run here. And we look back here and we see, okay, it's still reasonably flat. Our gain is gain seems to be a bit higher. So maybe I didn't do a perfect job of matching it, did I? 16 dB. But you can see some bumpiness there. And that's again why I want to have the bypass for the tone controls. Let's look back at my tone controls and so on, and I can point out some features that I wanted to be included here and that I've included because they were necessary. So in the initial circuit, first of all, this was only a 0.02 microfarad capacitor, and I've increased that to 2.2, and that's specifically so that I have really flat bass response in my bypassed version. The original circuit seems to produce a bump in the bass and then takes it back out later on, and it's a bit of a pain in the butt, not something I really want. So I've just beefed up that capacitor so that I'm not filtering out lows out of the input straight out of the gate. Again, I've got my feedback network here and a very small value, just 4.7 picofarad bypass capacitor on the feedback. That's so that at high frequencies, the feedback will be much greater, or will increase at high frequencies, and specifically the minus 3 dB point for the amp turns out to be right around 70 kilohertz, which is what I wanted. And what that does is prevent me from getting oscillation, or the tendency towards oscillation, at around 100 kilohertz, which is, I don't know if I'd say that's a common problem, but it's a problem. It can be a problem with tube amps. Now, this is my tone control circuitry down here, and I've got these, I've got the tone pots set to approximately their middle positions, but in any case where it's reasonably flat. I've changed some of the capacitance values and some of the resistance values. Specifically, I've cut out this 20 picofarad, which, like I said, I may put back in. I have changed these values over here. These were 0.0, these were 33 nanofarads and these were 30 nanofarads and 3 nanofarads, and I've changed it to 3.3 and 22. And that's because it just seemed that that was what was needed in this circuit to get it flat at a flat setting. I've also increased this resistance from 15K to 18K. So relatively modest tweaks to the circuit to get it better behaving, and then adding the tone control bypass. And you know, like I've been testing it at different volume settings, with the loudness on, with the loudness off, as it is now. I discovered the need for this bypass capacitor here in switching the loudness. So for example, let's see, let me just show you that, because that could be interesting. And we'll switch on the loudness control, which it's set at pretty high volume, so there shouldn't be a lot of need for loudness in the circuit. Oh, and over here I want to go back to my flat circuit, or my tone bypass. So I've got loudness on, which I, you know, if with tone bypass, or typically I would probably not have the loudness on, but I could still have the loudness on, and I want to make sure that it functions reasonably well when in that condition. And so here we go. So we've got this pretty big bump in the treble here, and that is similar to what we see in the default circuit, in the original circuit. But without that bypass capacitor in there, this peak here can get quite high. Now, it is above audible, right? Here's 20 kilohertz right here. So that peak is above audible, but I just don't want it getting too big and causing problems. Because one thing about as I alluded to before, the computer model doesn't account for everything that's really in the circuit, including stray capacitances and some quirky behaviors of tubes. So, well, anyway, I think that probably about does it. I've been utilizing this computer modeling in order to help me with this work. And it is very helpful because it allows you to do a bunch of tweaks, try a bunch of different things without actually having to deal with wires and parts and so on. All right. Well, subscribe to the channel if you haven't, and if you want to, give me a like, give me a comment, and I will talk to y'all later. Cheers.